Hey guys, Mr. Smith here. And in this video lesson, we're going to be proving some trigonometric identities. In your grade 11 course, you guys prove some identities using some of the basic identities that you learned in grade 11, the Pythagorean identity, the quotient identity, and reciprocal identities. And we're just going to kind of take these things to the next level in this lesson. Should be good. Let's get started. As a little bit of a little bit of a motivation on why identities can be useful. So those of you guys who have taken grade 12 physics or are taking it, or maybe you did this in your grade 11 physics course, but when you have a projectile and you launch the projectile with a certain initial speed v at a certain angle theta, and if you have a certain acceleration due to gravity g, then you can actually model how far the horizontal range of that projectile is going to be. Like, so essentially where it's going to land. In this question, they frame it this in terms of an aircraft in a parabolic arc, and the kind of the horizontal range is like the width of this parabolic arc, and you'd like this to be as wide as possible. Or if you were a football player kicking a field goal, you'd want to launch it at an angle that makes the football go as far as possible. And an equation, and you can maybe in physics you derive this, an equation for this width, this range, is 2v squared over g times the sine of the launch angle times the cosine of the launch angle. And maximizing this expression can be a little tricky, but you can actually simplify this equation using an identity that we'll see later by using this double angle formula, and we'll prove this later. You can replace 2 sine theta cos theta with the much simpler sine 2 theta to get more simply 2v squared over g times the sine of 2 theta. And actually, I think, well, I know actually, this is just a typo in the textbook. There actually shouldn't be a 2 there. It should just be v squared over g sine 2 theta. But why would you consider this simplified? So what if you were trying to find the angle that maximizes this w? Well, using the simplified expression, we know that sine of 2 theta has a max when the angle inside, when 2 theta is equal to 90, or when theta is equal to 45 degrees. And that's it. Using sine 2 theta, it's that easy to say, okay, this width will be maximized when the angle is 45. That's not so obvious when you're trying to maximize the product of sine theta times cos theta. It's not obvious at all. So these identities are often used to simplify expressions for us to make our life easy. That's why we're doing them. We're not doing them just to have one more thing for you guys to memorize or one more tough thing for you to do. They can be very useful. So let's dive in here. So here I've got an equation, and we've looked at a few identities so far, and this one's brand new. But what we're asking in this question is this equation actually an identity? Is it true for all values of x, or is it true for only some? So let's dive in here. We're going to first see if this equation holds for x equals 0. So the way we'll do that is we'll plug in 0 on the left. So we'll have the tan of 0 plus pi by 4 is pi by 4. And the tan of pi by 4, tan of 45 degrees, is exactly 1. How about the right side? We have the sine of 0 plus the cosine of 0. Sine of 0 is 0. Cosine 0 is 1. It equals to 1. That's not enough to say that equation is true for all values of x. We only showed it was true for 0. Let's see if it holds true for pi by 4. So here we're doing the tan, the left-hand side. The tangent of pi by 4 plus pi by 4, which is 2 pi by 4 or pi by 2, or 90 degrees, right? And the tan of pi over 2, or the tan of 90 degrees, is actually undefined. You do that on a calculator, it's going to give you an error message, right? Well, let's see if the right-hand side is undefined. The right-hand side is the sine of pi over 4 plus the cosine of pi over 4. And using our unit circle, our special triangles, we know that's 1 over root 2, or root 2 over 2 plus root 2 over 2, which is equal to 2 root 2 over 2, which is just root 2. So we can see, actually, no, this equation isn't an identity. It's not true for all values of x. It might be true for some. For example, it was true when x is equal to 0, but it wasn't true when x is equal to pi by 4. So you can verify if an equation is an identity by plugging in values and just checking out some values. So the key idea is this. To show that an equation is not an identity, you only need to find don't know why I have a period there, but you'll need to find one counterexample. If you can find one value that makes the left-hand side not match the right-hand side, then you've proven it's not an identity. So we only need to find one counterexample. Okay, so if you're just, if you want to see if that's an identity or not, just try some values. If you find one value that makes the equation not work, you're done. It is not an identity, because remember, identities have to hold for all values of x. It's an equation that's always true. So that's one way that you can show that an equation is not an identity. Another way would be to graph each side of the equation. And I have Desmos loaded up, so I'm going to hop over to Desmos. Here we go. And our first one is tan of pi by 4. And I believe that I am in working with radians. Oh, it's tan of x plus pi by 4. Excuse me. And as I've mentioned, like we've been graphing some trig expressions. We're going to go into detail about how these graphs arise in our next unit. Yeah, there's the graph of tan of x plus pi by 4. How about sine x plus cosine x? What's that look like? Sine x plus cosine x. Okay, so clearly those are not equal. They're equal for some. Like, for example, at 0, each side gives you 1. And it also looks like those two sides are equal if x is negative pi by 4, negative pi by 2. The next one is 3 pi by 4. So there's lots of values for which they are true, but there's many which they aren't. And you only need to find one. Also, a visual representation can also show you that they're not equal. All right, let's head back. So we've talked about how to kind of disprove and show something's not an identity. But when we want to show that two things are an identity, just plugging in a bunch of numbers, and even if we get like 10 numbers that work, it's not enough. It's not a formal proof. Even if we graph two expressions and they look to be the same, it's not a formal proof. They might not be. That graph might only have certain parts of the domain. So to prove an identity is true, and you guys did some of this in your grade 11 course, you have to show that one side equals another, kind of like algebraically. Or that you can manipulate both sides into the same thing. For the rest of this lesson, we're going to prove a few identities. We're going to bring out a variety of skills, and we're going to use some of our old friends. So on the left here, you've got the identities that you developed in your grade 11 course, the Pythagorean identity. The sine squared of an angle plus the cosine squared of an angle is always 1. Tangent is the tangent of an angle is the sine of that angle divided by the cosine. And then you have your reciprocal identities you developed in grade 11 as well. We also might mix in today some of our compound angle formulas, which we derived and we summarized in our last lesson. So just have these handy. You have them several other spots in your notebooks. And here they are for the lesson ahead. They're on your lesson sheet. All right, let's dive in. I always like proving identities. I find each one's like a little bit of a puzzle. And if you have any good ones, send them my way. Love proving identities. So here is one. If you if you're watching this lesson, you would have done the video assignment in our for this unit, um, where you had to prove a double angle formula. And maybe the one you proved was that sine 2 theta is equal to 2 sine theta cos theta. We're going to prove this one by taking the left-hand side and making it look like the right-hand side. So we're going to take sine 2 theta. And the trick with this is we're going to write 2 theta as just theta plus theta. So we can apply our compound angle formulas. So sine of something plus something else is sine cosine plus cosine sine. So this will be equal to sine theta cosine theta plus cosine theta sine theta. And that was a compound angle formula. If you're wondering how we got there, well, if you want to get that in there, so when you're studying later from your notes. And here we have sine theta cos theta, we have cos theta sine theta. They are the same term, and we can add them together. We get 2 times sine theta times cosine theta, which is equal to the right hand side. And we've proven our identity. So that's pretty cool. Let's just verify this one in Desmos, and I think that'll be the last one we have a look at in Desmos today. But yeah, feel free to always double check. So we'll graph sine 2x, and then we're going to graph, so that's it in red right there. And then the graph of 2 times sine x times cosine x. I think it wants me to use brackets. I'll do that. Interesting graph. All right, that's better. And you can see that, sine 2x is in red, 2 sine x cos x is in blue. They're the same graph. And moreover, we actually proved it algebraically that they are the same expression. That is an identity. So pretty neat. Let's continue. Here's one of our cofunction identities that we developed a couple lessons ago. Let's actually prove it's true. And we can do that using one of our compound angle formulas. So this is another one where we're going to take the left-hand side and we're going to manipulate it and make it look like the right-hand side. So cosine pi over 2 minus x. Here we go. So our compound angle formula for cosine and subtraction is cosine cosine plus sine sine. So that's cosine of pi over 2 times the cosine of minus x, and then plus the sine of pi by 2 times the sine of minus x. All right, now the cosine of pi over 2 is 0. So this whole term is gone. And the sine of pi by 2 is equal to 1. Now I might show an extra step here. If you feel comfortable in your notes, maybe you don't have to show this, but cosine pi over 2 is 0. Sine pi over 2 is equal to 1. So that's just equal to the sine of minus x. All right. And in our case here, why did we get... I'm just going to pause the recording. I feel like we should have got, or for some reason it's not quite working out. We'll check back in 1 second. All right, guys. I had to stare at it for a second or so, and then I realized in our identity for cosine, if it's cosine x minus y, it's just cos x cosine y. For some reason, I kept including the negative. So let's just fix this up here. My eraser tool. Oh, it's just a cosine of x, and it's just the sine of x. That was a silly mistake, but we figured it out. and that just gives us sine x. So yeah, you can prove your cofunction identities by using the compound angle formulas that we developed in our fourth lesson. So that's pretty cool. Let's look at another one. So let's look at a identity involving reciprocal ratios. Now, I have a lot of space on here, so I'm going to show in the previous two examples, I took the left-hand side and I made it look like the right-hand side. In this one, I might do both, just because I have a lot of space. And because this lesson is it's on the shorter side, so I feel like I can squeeze an extra something in. Let's have a look here. What's the left-hand side? How can we manipulate that? Well, one strategy you guys would have learned in your grade 11 course is if you're proving an identity and you see these reciprocal ratios, one common theme is just to actually rewrite that using the definition of that reciprocal ratio. And cosecant is the reciprocal of sine. And that's just using a reciprocal identity. All right, and now we can make use of this double angle formula for sine. We know that sine of 2x is equal to 2 times sine x times cosine x. That's one of our double angle formulas. And now I'm going to break this up into 1/2 times 1 over sine x times 1 over cosine x. And if you look at each of those terms, 1 over sine x and 1 over cosine x, so there are reciprocals. But look at our right-hand side. We've got a 2 on the bottom. We've got a cosine x on the bottom. And 1 over sine x is equal to cosecant x. So this is equal to, I'll show a lot of extra steps here, times cosecant x times 1 over cosine x, which equals to, if we just clean that up, cosecant x all over 2 times cosine x, which is equal to the right side. So we've proven this identity. We've taken the left-hand side and we've made it look like the right-hand side. But here's what you could do too. There's nothing wrong with starting from the right-hand side. If you think the right-hand side is a bit easier to manipulate, then go for it. There's definitely more than one way to prove an identity a lot of the time. Okay, so in this question, we're going to apply the same idea. You see cosecant, you think, okay, I'm going to replace cosecant with 1 over sine. So I'm going to do that here. But I'm going to kind of show an extra step, not really necessary for you at home, but just since this is one of the first ones we're doing, I'm going to rewrite that as cosecant x times 1 over cosine x. And I know that cosecant is 1 over sine. 1 over 2 cosine x. I can multiply those together, and I get 1 over 2 sine x cosine x, which I know using my double angle formulas, that's 1 over sine of 2x. And using my reciprocal identities, I know that's cosecant of 2x. And that equals the left-hand side. And we've shown that the two sides are equal, but we used different strategies. So what do we do? I might just add, so in this step, we made use of our reciprocal identities. This step here, we made use of our double angle formula. And then we use our reciprocal again at the end. But yeah, more than one way to do it. Whichever way you feel, if you kind of see a strategy, then just carry it out. And sometimes some people might prefer to work with the left in a question like this, and some people might prefer working with the right. But either way, we've shown left side and right side are equal. Pretty cool. All right, let's do another one. We're at 2 more. All right, so this is a more complex identity. So just off to the right here, just some skills that you might need when solving more complex identities. Sometimes factoring might be involved. Sometimes adding or subtracting rational expressions might be involved. And it's hard to cover every single type of question. So I kind of picked this one out. The Nelson text had this in the chapter, and I thought it was a fine one to do. So cosine x plus y times cosine x minus y equals cosine squared plus cosine squared x plus cosine squared y minus 1. It's a pretty cool looking one. And let's dive in. We're going to solve this one by starting with the left-hand side. And I look at the left-hand side and I see cosine x plus y. I see cosine x minus y. And for me, that's a clue that maybe I should be applying my double angle formulas for cosine. So cosine x plus y is cosine cosine minus sine sine. So it looks like this. So it'd be cosine x times cosine y minus sine x times the sine of y. And then cosine x minus y is equal to cosine x cosine y plus sine x sine y. And that was from our compound angle formulas. All right, now we're going to clean this up a little bit. We're going to expand and simplify, but let's just do this kind of intelligently, save ourselves some work. Notice what we have here is essentially a difference of squares: a minus b, a plus b. So when we do the expanding, we're going to get cross terms that add to 0. You're going to get cosine x, cos y, sine x, sine y as one term, and then negative cos x, cos y, sine x, sine y. And they're going to add to 0. And what you'll be left with is a squared minus b squared, just like in a difference of squares. So we're going to get cosine squared x times cosine squared y. And we're going to get minus sine squared x times sine squared y. All right. And again, that just is kind of using a difference of squares pattern. Right? That gives you like a squared minus b squared. Okay, where to next? I'm looking at the right-hand side. I see cosine squared x by itself, cos squared y by itself, and 1. And I don't see any of that happening right now. So another trick is, if we're looking at the right-hand side, we can see it's in terms of cosine squared. Let's take our expression here and let's write all the sine squareds in terms of cosine squared. And we can do that using the Pythagorean identity you guys learned in your grade 11 course. So I can rewrite this as cos x squared, cos squared y, minus sine squared is 1 minus cosine x squared. Sine squared y, 1 minus cosine squared y. And this is using the Pythagorean identity. And now let's expand and clean this up a little bit and see what we get. So we have cos squared x, cos squared y, minus, so we're going to have 1 times 1. We're going to have minus cos squared y. We're going to have minus cos squared x. And we'll have minus times minus. We'll have plus cos squared x cosine squared y. Aha, and maybe you can see where this is going. In fact, we're basically done here. Cosine squared x times cosine squared y. And we're going to be subtracting the same thing. They're going to subtract to 0. And then if we distribute in this negative, we're going to get negative 1, positive cosine squared y, and positive cosine squared x, which is exactly the right-hand side. Equals right-hand side, done. So look to use your double angle formulas. Look to use your Pythagorean identity when you can. Those are just a couple good strategies in general. Again, you might have to apply some factoring techniques. Like in this case, when we were expanding, we recognized that cos squared x, that this was a difference of squares. And again, for identities that involve some rational expressions, you might have to add or subtract some rational expressions too. All right, I've got one more for you guys. And I just thought this was kind of a cool one. And I wanted to do one where we take the left hand side, make it look like something, and then take the right hand side and make it look like something too. And because in all the other ones we've done so far, we've taken the left hand side or right hand side and make it look like the other guy. So let's check this out. Here on the left hand side, we've got cosine to the power of 4 minus sine to the power of 4. So I mentioned that you might have to use some factoring strategies. This is a difference of squares. Cosine 4x is like cosine squared x squared. So I can write this as cosine squared x plus sine squared x. Sine squared times sine squared is sine to the power of 4 times cosine squared x minus, I forgot the x, minus sine squared x. That's just factoring. But look, guys, cosine squared x plus sine squared x, that's just equal to 1, right? And we're just left with cos squared x minus sine squared x. We're going to use that Pythagorean identity. Sine squared plus cosine squared is equal to 1. I might just take a different color here and show that all of this is just equal to 1. Okay, so right now, not immediately clear how I can make that look like the right-hand side. So what I'm going to do is I'm going to take the right-hand side and I'm going to start manipulating it. So cosine 2x, we can write as the cosine of x plus x. And let's use that identity. So cosine of x plus x, just refreshing myself. Again, I don't have these memorized. Don't know many people that do. Just reference them when you need them. So it's cosine minus sine. That's cosine x times cosine x minus sine x times sine x. Hey, wait a minute. That's equal to cosine squared x minus sine squared x. So we've taken the left-hand side and the right-hand side kind of separately, and we've shown that they equal the same thing. We have actually shown here that the left-hand side is the right-hand side. So I wanted to do one with you guys where we manipulated both sides to get to the same thing. And just to show you guys that that's okay. It doesn't happen all the time, not needed all the time, but I thought I would share that with you guys. All right. So we've proven, I think, 5 identities together. Time for you guys to practice applying some of these skills. This actually wraps up our first unit on trigonometry. Our next unit, we do more with trigonometry, but it's more focused on the graphs of trig functions and solving trigonometric equations. So the things we did with polynomial functions and rational functions, we're now going to do that with trigonometric functions. Look at some basic graphs, do some transformations, solve some equations, solve some inequalities. Also, we're going to look more detail. I've kind of shown you guys a few of these graphs. We're going to look at what the graphs of tangent, cosecant, secant, cotangent are. But for now, got some suggested practice for you guys. As usual, do as much as you need to feel comfortable. Make sure you're checking out the solutions manual if you're stuck on something or want to check an answer. Also, you can reach out to me if you need a hand. But yeah, guys, that's it for this video lesson. Hope you guys are staying well. Take care. We'll see you soon.